For the next talk, I would like to welcome Professor Rukmini Dey from ICT-STIFR Bangalore campus, and she's going to tell us about minimal surfaces.
I would like to begin by thanking the organizers for inviting me for this great celebration. It's really an honor for me to be here. And so today I'll be talking about minimal surfaces. I'll just put this here. Today I'll be talking about minimal surfaces because when we are children, we have always played with soap films and soap bubbles, and without knowing that there is such beautiful mathematics behind it. And some of you already probably know what I'm going to talk about, but and also it's not going to be very rigorous because I'm trying to address a mixed audience. So I'll be talking about this beautiful surfaces. So before we start, topology of compact-oriented surfaces are classified by their genus. The genus 0 surfaces, are these spheres, right? Or ellipsoids, or these are the genus 0 surfaces. These are genus 1. This is triple torus, so genus 3. So to a sphere, you keep adding handles, and that kind of gives you the genuses, the holes through these. These are genuses. And there's a beautiful formula of Euler, which says if you can divide it up into how do I go back? Oh. Yeah, so if you can divide up the surfaces into faces, into vertices, I mean you divide it up into faces, certain number of vertices and edges. So then V minus E plus F is equal to 2 minus 2G for a compact oriented surface. So if you can, for example, the sphere, if you can break it up into, like for example, a cube. Cube is actually topologically the same as the sphere, and if you calculate V minus E plus F, you will get 2 minus 0. And similarly for all the Platonic solids. For example, for the octahedron, tetrahedron, octahedron, dodecahedron, icosahedron, if you calculate V minus E plus F, you will find it's just 2, right? And for the plane, for a triangle, you will see V minus E plus F is 1. And Mobius strip, this is and then I just wanted to, show an example of a non-oriented surface with a boundary. And this is a Mobius strip, and it comes up in minimal surfaces a lot. So this is one thing. And so that was topology. What I was talking about is when you don't really care about you don't care about continuous deformations, right? Like you can squish a ball into a ellipsoid, and topologically they'll be equivalent. But now we start to care about the details a bit. So that is geometry. So we talk about lengths of curves on surfaces, area of the surface, Gaussian curvature, mean curvature, etc. Sphere and ellipsoids, though topologically they are equivalent, they are very different in this sense. For example, the sphere is totally symmetric while the ellipsoid is not. So here geometry plays a role. So minimal surfaces is more about geometry rather than topology, and we will see very soon some pictures of those. So parametrized surfaces in R3. So in our entire discussion, we will be using parametrized surfaces in R3. So X in this bold is X of UV, Y of UV, Z of UV. UV are two parameters which are locally describing the surface. Okay. For example, if you take Z is equal to tan inverse Y by X, this is actually a surface called the helicoid, and you can parameterize it in many ways. For example, u v tan inverse v by u, or r cosine theta, r sine theta, theta, right? But then we can also introduce a very novel parameterization in terms of complex numbers. So you take zeta to be u plus iv, and you can just write x of uv as x of zeta zeta bar, y of zeta zeta bar, z of zeta zeta bar, where x is of the form minus half imaginary zeta plus 1 over zeta, y is half real part of zeta minus 1 over zeta, and z is minus pi by 2 imaginary ln zeta. If you solve this, you will get exactly this equation, z is equal to tan inverse y by x. So why am I talking about this kind of parameterization? And okay, the parameterization fails for zeta is equal to 0, as you can see. So this kind of parameterization holds because the helicoid is actually a minimal surface. So we will see parameterizations like this occur, like x is real or imaginary part of a holomorphic function, y is real or imaginary part of a holomorphic function, z is a real or an imaginary part of a holomorphic function. They are what are known as harmonic functions. Okay, so this kind of parameterization occurs if the surface is a helicoid. So that's, I'll come to that. So what are minimal surfaces? We'll be talking about these surfaces which appear in nature as idealized soap films. They are stationary points of the area functional. Locally they are area minimizing, or a saddle point of the area functional. So you can see these soap films, we have played with these as children, right? So and the mathematical property is the mean curvature is 0 at every point. So for all those who know what about this curvature, the principal curvatures, so if K1 and K2 are the two principal curvatures, then K1 plus K2 equals to 0. And if K1 and K2 are non-zero, then you know the principal curves, the principal lines of curvature curve in opposite directions. If one of them curve like this, the other one curves like this. So it's actually a saddle at every non-umbilical point. And they have negative or 0 Gaussian curvature. Umbilical points are where the Gaussian curvature is 0. Soap bubbles, however, are not minimal surfaces. They have constant mean curvature at every point, not 0 mean curvature, non-zero constant mean curvature every point. And they are actually part of this huge topic called integrable systems. The constant mean curvature surfaces are very difficult to, they are much harder to describe. The sphere, cylinder, these are very simple examples. Okay, back to minimal surfaces. For example, this helicoid and the catenoid, they are actually related. Later on we'll see actually they are related. And so this is the helicoid, this is the catenoid. Catenoid is got, you take a catenary, revolve it about this axis, you will get a catenoid. And helicoid you have seen as spiral staircases. And this is the N-apple surface you have seen in potato chips, this is the shape. And this is another type of N-apple surface. These are the shark surfaces. This also will come up in my talk later on. This is the shark's second surface, this is the shark's first surface. And again they are also related in some ways. I mean, we'll see. There is a way of going from one to the other through a family of minimal surfaces. And then there is this is the genus 1 Costa surface. It's an immersion of a torus with 3 punctures. You take a torus, take 3 punctures, and you can immerse it in R3 using some number theoretic functions called Weierstrass P functions, and this is how it looks like. So believe it or not, there is only one genus and there are 3 punctures. The 3 punctures have opened out as 3 ends, like these 3 ends. And then there is the Riemann staircase. this is the genus 1 and multiple genus helicoids. And this is a triply periodic minimal surface which appears in crystallography. So sometimes since the audience is diverse here, like equipotential surfaces in crystallography are minimal surfaces often. Like if you have crystals and there could be a surface through those molecules such that there is no force on it, right? You can imagine a surface such that all forces are like balanced on that surface. That turns out often to be a minimal surface. So in crystallography also these appear. Okay, Plato's problem for the layperson. So given a small closed wire, if you dip it in soap solution, is there a soap film spanning it, and if so, how many? So Douglas gave an answer to this, Jesse Douglas, he got the first Fields Medal for this. Douglas gave answer to the mathematical formulation of this question. He said yes, and subsequently this has been an active field of research. And the question of how many minimal surfaces span a given curve has been studied by Tromba using catastrophe theory. So here I was telling you about the Mobius strip. So you have a Mobius curve, you dip it in soap solution, you can get these kind of surfaces. This is one type, this is a second type. Okay. So actually the number of, if you dip a soap, I don't know if you have played with wireframes and soap solutions. If you dip it in, if you dip a wireframe in soap solution, you may not get a unique soap film spanning it. There could be various soap films spanning it. So let us go into the little bit into the mathematics behind it. So if you can write your surface locally as xy phi of xy, then the mean curvature 0 equation is actually quite a complicated PDE. 1 plus phi x squared phi yy minus 2 phi x phi y phi xy plus 1 plus phi y squared phi xx equals to 0. It's a complicated PDE, but the nice thing about this is in isothermal or conformal parameters, if you choose your UV properly, you can write it as x of uv, y of uv, z of uv, conformal parameters, and in these coordinates just the equation, the x, y and z just becomes Laplacian of x equals to 0. So in each coordinates, each coordinates become harmonic functions in these special UV coordinates. So finding the conformal parameters may be difficult, but if you can get conformal parameters, then this complicated equation just becomes harmonicity of the coordinates. So this is I have written here what is the conformality condition. Norm xu equals to norm xv and xu xv are orthogonal. Okay. So that kind of harmonicity of coordinates means you can relate it to you can immediately relate it to complex analysis, because real and imaginary part of holomorphic functions are harmonic. Okay. So, and also from that it follows that complete minimal surfaces cannot be compact. So for example, a torus can never be thought of, never be immersed into R3 as a minimal surface. You have to remove certain points. For example, torus with 3 punctures as I showed. Okay. So, and then the most general solution of that equation is zeta is u plus iv, zeta bar is u minus iv, then you can write x of zeta bar in this way, y of zeta bar in this way, and z of zeta bar in this way, where f and g, f is holomorphic, g is meromorphic, such that fg squared is holomorphic, and so basically what I am saying is holomorphic is it doesn't depend on w, it just depends on w, it doesn't depend on w bar. Okay. And in that case you can actually choose your favorite f and g such that f and g are, f is holomorphic, g can be meromorphic, but fg squared is holomorphic. In that case you can construct, this is going to be always a minimal surface. So you can take your favorite one, okay. Favorite FNG, only restrictions are these. So there's another way of writing it. In a neighborhood of non-umbilical point where the Gaussian curvature is non-zero, any minimal surface can be represented in terms of a non-vanishing meromorphic function. You can actually choose your favorite meromorphic function, and meromorphic function are holomorphic, but they can have poles. They are allowed to have poles. Okay. So they depend only on W, but they can have poles. So so any minimal surfaces can be represented in terms of one non-vanishing meromorphic function like this. Again, this is always going to be a minimal surface, and you can pick and choose your R. For example, R is equal to 1 corresponds to the NEPA surface. This corresponds to the catenoid, this corresponds to the helicoid. So all you have to do is pick your favorite R and perform the integrals to get your minimal surface. Okay, I am not going to go into all these details. So finally, I wanted to tell an interesting fact which me and my collaborators have found, how Ramanujan's identities are also coming in minimal surface theory. So here this is a Scherk surface, type 2, and this is type 1 Scherk surface, right. So here I have actually performed the integrals and shown. So this was for the helicoid. After performing the integrals, you get that representation I was talking about initially. Before going into Ramanujan identity, there is a beautiful fact that there is a whole family, isometric deformation from the helicoid to the catenoid, such that this, at every stage, it's a minimal surface. So you see the topology is changing. Here the helicoid has a very different topology from the catenoid, but you can still deform, go from one to the other through a family of minimal surfaces. So that's why this is called the conjugate of this. In some sense, they are actually conjugates of this. So I'm not going into the theory. Similarly, this one and this one, actually there is a way of going from one to the other through a family of minimal surfaces. I have not shown the picture. Actually, I don't have the picture of that. So, okay, finally, how much time do I have? 10 minutes. Okay, good. So, a geometrical interpretation of an identity of Ramanujan. Actually, Euler-Ramanujan I should put. Euler also used to know this. So, tan inverse tan h y cot x is summation k goes from minus infinity to infinity tan inverse y by x plus k pi. Okay. So this is a Euler-Ramanujan identity. This is one of the identities, but the amazing thing is this left hand side is a height function of a minimal surface. Z is equal to tan inverse tan h y cot x is one way of writing this red, maybe I have the picture later on. This one can be represented like that. The height function is tan inverse tan h y cot x is the Scherk's first surface, and these you already tan inverse y by x you already know is a helicoid, and these are just shifted by k pi. So I have shifted an array of helicoids and added the height functions, okay, and I got a minimal surface, which is not to be expected at all from a very nonlinear complicated equation, right? So this is what one of the identities give, and this was used by a condensed matter physicist and his collaborator Randall Kamian of UPenn. So we have used this for some other things, and recently also me and my collaborators, we have found finite decompositions. So for example, z of xy is equal to ln cosine y cosine by cosine x. This is this one, the other Scherk surface, the one with tunnels. What was it? This one. this is the one which is given by z is equal to ln cosine y by cosine x. Okay, and that also is part of a Euler-Ramanujan identity, because this is the identity of Ramanujan. Okay, cosine of x plus a by cosine a is this. So if you take ln on both sides, you take x plus a to be y and a to be x, then you can get this kind of an identity, and this is the height function of that tunnel-like minimal surface, right? The Shark's second surface. And what we did was to cleverly rearrange this, just a clever rearrangement of these sums. These sums, instead of k goes from 1 to m, we just write it as k n np plus m, and we could rearrange it to get that there is a finite decomposition also. So z of x comma y, which was this, is summation m goes to 0 to n minus 1, z by x by n minus some constant, y by n minus some constant. So up to translations and scalings, what we got is Shark's first surface can be decomposed as finite sums of height functions of the same type. Though these are not exactly minimal surfaces, but they are scaled ones. So if you just took 1 over n here also, then it will be a minimal surface. So if you look at the minimal surface equation, if you scale x by x by say alpha x, scale it by alpha, y also is scaled by alpha, z also is scaled by alpha, the equation remains invariant. So almost minimal surfaces which look like the Shark's second surface, so the height functions can be finitely decomposed. So, and the other thing which we are working on is how close this so Douglas's work shows that there is a very interesting interpolation problem. So you can ask, given two real analytic curves or just Jordan curves, say simple curves, okay, then how close should they be so that there is an interpolating minimal surface. Okay, so supposing you have two wireframes, I am dipping it into soap solution. If you put them very far apart, energetically it will be more suitable for it to have two independent disconnected parts. But if you bring it close together, then actually energetically it's better to have it will prefer to have an interpolating minimal surface. So we actually used some inverse function theorem in infinite dimensional setting and Bjorling-Schwarz problem, so to show how close they should be. And secondly, we are also trying to work on maximal surfaces in Lorentz-Minkowski space where this Plato type problem has not been solved, and we could get this kind of interpolation by those maximal surfaces using the same method. So it's only existence results so far, but we are trying to get many examples. So that is this thing. And so if anybody wants to get into minimal surfaces, there are very beautiful work. So first is Manfredo Doccarmo's Differential Geometry of Curves and Surfaces. That is a very basic, beautiful book on curves and surfaces. Then Osserman's book of Survey of Minimal Surfaces, Dierkes and Hildebrand, Kuster and Bolrav. Then Nietzsche, Witham, Ramanujan, Lopez, all these that are very, so this is what I was saying, the maximal surfaces in Lorentz-Minkowski space, if anyone wants to get into that. And so me and my collaborators also have a lot of work on this direction. And this is the one I was talking about, finite decompositions of height functions, not only of minimal surfaces, maximal surfaces, Born-Infeld solitons, time-like minimal surfaces. And so what we find is they have similar kind of nonlinear equations, but you can still decompose the height functions into scaled and translated versions of itself. So, solution, yeah, so that's it. Thank you.
Thank you, Professor Dey, for nice talk and interesting pictures. We have a small token of appreciation.
Thank you so much.